Okay, hi everybody. I'm Sylvie. I was working in the Moore lab this summer, and I'm going to be presenting about cooling a magnetogravitationally levitated water droplet. So first, to give some overall background about what our lab does, we're using levitated mechanical sensors for nuclear and particle physics. And more specifically, we're using levitated nanospheres and microspheres as these sensors. So essentially what we do is we embed or plate a radioisotope onto these levitated spheres. And then when nuclear decay events happen, it produces a momentum kick, which we can detect by measuring the position of the sphere using lasers. And then using this known momentum kick or this measured momentum kick, we can then use conservation of momentum to reconstruct, hopefully in the future, the mass of the emitted particles from this nuclear decay. And this is one of levitated nanospheres that's optically levitated. So the main driving question behind my project was how do we get these radioisotopes into these levitated spheres? And we have done this successfully previously, but it was using a specific isotope with a specific technique that wasn't scalable to other isotopes that we might be interested in. So there was two new techniques that we wanted to examine. The first technique involved plating the radioactive gas onto the outside of the sphere by first cooling the internal temperature of the sphere, blowing the radioactive gas at the sphere and having it freeze onto the surface. And then the second method would be to freeze a levitated sphere with the radioisotope already inside of it. So trapping a liquid droplet with this radioisotope and then freezing it by lowering the pressure to freeze it through evaporative cooling. So my project was to develop a test setup to test both of these techniques. I used a levitated water droplet and I used a magnetogravitational trap. You can see this is the levitated droplet here, and these are parts of the magnetic trap that I'll talk about in the next slide. But after trapping this water droplet, I then designed a cold gas delivery system to cool the internal temperature of the sphere, which is testing method 1 that I talked about previously. And then I also integrated the trap into a vacuum chamber to be able to pump down the pressure and cool through evaporative cooling, which is method 2 that I talked about previously. This trap was designed by one of the grad students in our lab, Sanok. And this is a little bit of background about how the magnetic trap actually works. You can see here that it's made up of two permanent magnets and then these 4 pole pieces. So these pole pieces are configured in a quadrupole formation, and they create a magnetic field with variable strength. And this magnetic field gradient, which this is the x and y axis, this is the x and y axis here. This magnetic field gradient, along with the gravitational potential energy, creates a 3-dimensional potential well in between these pole pieces, so in the center of the trap, which is where the water droplet wants to sit. And the reason that this works is because water is a diamagnetic material, which means when it's placed in an external magnetic field, a magnetic field is induced inside of it, which opposes that magnetic field. So this allows the water droplet to be levitated in between these pole pieces. And the way we get the water into the trap is by nebulizing it into the trap. So this is what a nebulizer looks like. Essentially, it just creates a very fine water mist by pushing water droplets through a fine mesh screen. This is a video of me actually nebulizing the droplets into the trap. Okay, and then not put. Anyways, essentially I just mist this water mist into the trap until I can slowly build up this water droplet. And these are the pole pieces that I talked about previously in the magnetic trap. So then I moved on to actually assembling this cold gas delivery system. So I used nitrogen gas. The nitrogen gas came out of this nitrogen dewar, then passed through a multi-valve system, passed through a copper coil, which was sitting in a liquid nitrogen bath, and then before running through a nozzle and blowing out the nitrogen gas at the trapped droplet. The reason we have it running through this liquid nitrogen bath is to significantly cool the nitrogen gas before blowing it onto the droplet. And we measured the temperature of the position of the droplet using thermocouples as our temperature sensors. These are some photos of my actual setup. Here's that liquid nitrogen bath with the coil inside of it. This chamber is where the trap is located itself. And then this tubing has the nozzle, which is pointed directly at the trap. this is like a little bit of an up close. You can see the nozzle opening pointed directly at our trap. These are those pole pieces, and then we have the water droplet located right at the center of this trap. So we found that the main constraint with this method was the mechanical stability of the droplet. Essentially, when we blow the gas at the droplet, the stronger we blow the gas, the more likely we are to knock the droplet out of the trap. So this restricted our cooling ability. Blowing more cold gas knocked the droplet out. Blowing less cold gas didn't cool the droplet as much. And we also found that the gas jet was being heated up from the ambient air. So as it left the mouth of the nozzle and moved farther away from the nozzle, the gas jet was gradually getting warmer. So we found that with a stable trapped droplet with the flow that we could allow, we could get our temperature down to around 0 C on the nozzle side of the droplet and around 4 C on the other side of the droplet. However, we don't think that this was sufficient enough cooling to freeze the droplet because we didn't detect any optical changes in the droplet. So this brings me to the second method that I tried, which was to pump down the chamber and freeze the droplet through evaporative cooling. So first, to give some background on evaporative cooling, essentially when we lower the air pressure in the chamber, this lowers the condensation rate of vapor onto the droplet, which means that the evaporation rate is then higher than the condensation rate. And this net evaporation removes energy from the droplet. And this removal of thermal energy decreases the temperature in the water that remains in the droplet. So this is a phase diagram of water. You can see that at equilibrium, if we lower the pressure, we're also lowering the temperature until we hit the triple point, which is around 6 millibar. And then we get into the regime where we can freeze that droplet into solid ice. But one important thing to note here is that water can actually supercool past its freezing point. So we can lower the temperature lower than its freezing point before it actually crystallizes. And this is because without a nucleation site, the crystallization has essentially nowhere to start. So it can get very low, as cold as -48 C before this crystallization begins. So this was my setup for this. Pretty simple. This is the vacuum chamber where my trap is located in. And then I have a valve to control the flow to the vacuum pump. So we found that with this, the main constraint was that our droplet was actually evaporating away completely before we were able to pump down to a low enough pressure to freeze the droplet. So one thing we did was we added glycerol to the droplet. The water molecules want to bond to this glycerol, and it makes evaporation slower. So with this new method, we were able to pump down the chamber to about 10 to the -3 millibar with a stable droplet. And as you can tell from this phase diagram, which is of water and glycerol, 10 to the -3 millibar is right around here. So that's around 200 Kelvin, which means that we were significantly cooling this droplet and keeping it stable in the trap. But once again, we're unsure if this droplet was actually freezing. We're looking to improve the imaging on this droplet, but we haven't detected any optical changes yet. So where do we go from here? There are methods that we can use to improve the efficiency of both methods I talked about. First would be just to decrease the temperature of the nitrogen leaving the nozzle so that we're blowing even colder air at the droplet. Second would be to continue to decrease the pressure in the vacuum chamber so that we're further evaporatively cooling the droplet. Or, as I mentioned before, to improve the detection of freezing the droplet, either through better imaging or other detection techniques. But what we're looking at right now is actually combining these experimental setups to hopefully be able to be blowing in cold air through our nozzle while simultaneously pumping air out of the chamber. We're hoping that this could potentially decrease the heating of the gas jet from the ambient air. So if we remove the air particles, there won't be ambient air particles that are heating up this gas jet. And this will give us better thermal control at the position of the droplet, hopefully enough to freeze the droplet while it remains in the trap. So yeah, I'd just like to say thank you to Professor Moore and to my advisor, Sarah, for this summer. Yeah. Yeah, so right now we're using a microscope, looking at it through a lens and seeing if we can detect any optical changes. Yeah. So we're using the thermocouple. We have thermocouples placed just at different positions around the trapped droplet. So we're just using that to measure the temperature of the air surrounding the droplet. We can't actually measure the temperature of the droplet with using that method, but just to give us an approximation.
So one thing that because you are cooling the drop, you are changing the density on the drop, right? And cooling is done to the highest density. So do you have to adjust the magnetic field like in nature or the or it doesn't matter?
We adjust what? Sorry.
The magnetic field.
Oh no, so the pole pieces remain the same. The permanent magnets are always the same. Yeah, and the water will stay trapped in the diamagnetic trap. Yeah. Yeah.